In this video, we're going to talk about the drag force, and this is not something that we're going to use very often in this class. In fact, most of the problems that we are ignoring any effects of drag or air resistance. But the drag force is a force that is acting on objects as they move through any type of fluid. And so air resistance is an example of drag force. You've probably experienced air resistance if you've ridden a bicycle really fast or gone on a roller coaster, even if you're driving down the road with your window down, you put your hand out and you can feel that air kind of pushing up against your hand. So that is air resistance. That's the drag force, that feeling of the air pushing up against your hand. So the drag force is a force similar to friction. It's going to be a force that has a direction that is opposing the direction of motion. The drag force also is a little bit unique because it's not a constant force. So it actually is going to increase in magnitude as our speed is increasing. So it changes as a function of the velocity, and actually it's going to change as a function of the velocity squared. So it's highly dependent on the speed that our object is moving. We do have a simple model that we can use for the drag force, and anything that we're asked to calculate the drag force in this class, we will be able to use this simple formula. And so we have our drag force is equal to, we're given the magnitude piece, and then again, the direction is going to be opposite the direction of motion. So I'm going to run through just each of these variables in here, and then we'll do a quick example. So that drag force is 1/2 times c. And C is what we're going to call the drag coefficient. Let's see if I can write the word coefficient. Yeah, so drag coefficient. And the drag coefficient is going to be a number, it's a unitless number that is dependent on the shape of our object. And so I pulled these pictures from your book over here on the right side of the paper here, or the screen. So if we're talking about a sphere, so C is going to be 0.5. If we have something like a cylinder that is falling end down, so it's kind of vertically long ways, that C would be 0.8. And then if I have a cylinder falling side down, so the cylinder is kind of falling horizontal it's positioned horizontally as it falls, that C is going to be around 1.1. So that drag coefficient is going to be smaller for more aerodynamic shapes. Essentially, it's telling us something about the dynamicity of the object itself. Okay, so C is the drag coefficient. This variable here, this is rho, and in chemistry, you probably use D for density. In physics and many of your other classes, you are going to use rho. So this is a Greek letter rho, and this is just for density. And the density here is the density, I'll specify density of the fluid, right? And so if you're working with air, we commonly will use 1.3 kilograms per meter cubed as the density of air, just standard conditions. The A, that's going to be our cross-sectional area. So cross-sectional area of our object. And so that's going to be in meters squared. So that's an area. And then that V, that's going to be our speed. And that is meters per second. Okay, so our drag force can be calculated. So it's a function of all of these different things. So it's a function of the shape, that area that's basically contacting the fluid, right? So that cross-sectional area, whatever is hitting the fluid, the density of the fluid itself. So you can imagine the higher the density of the fluid, the higher the drag force is going to be. And then also the speed. So this model applies when the object is moving through the air near the Earth's surface. The object's size and diameter is between a few millimeters and a few meters, and then the speed is less than a few hundred meters per second. So again, anything that we're going to be working with in this class will fit within the criteria for this particular model. All right, so if we do this quick little example here, so I have, it says the profile of a typical 1,500 kilogram passenger car is seen from the front, and they give us some dimensions. So if I want to kind of imagine, so if I'm looking straight on the car, here's like my headlights, and Here's my little wheels. This is a terrible car, but here's the windshield. Okay, that's the front view of my car. So they're telling us that this is 1.6 meters wide, and then we're 1.4 meters tall. So basically that's going to give me an area, right? So I'm going to go ahead and just write that in here because I know in my equation I will need an area. So this is 2.2 meters squared. So then they also tell us we have aerodynamic body shaping is going to give us a drag coefficient. So they're going to tell us what that is. So that's 0.35. And that's less than our sphere, which is 0.5. So we've got a really nicely aerodynamically designed car, which is probably not the way I have drawn it there. But so we've got a drag coefficient of only 0.35. And they're asking us what speed does the magnitude of the drag equal the magnitude of the rolling friction? And then we also have the density of air. So I'll go ahead and write that in here. That's that 1.3 kilograms per meter cubed. Okay, so if we just think about the situation, so if we have a car, so I'm going to look at it now. This is like a front view, right? If I do a side view, then here is my, it would be much more aerodynamically drawn than this. But if this was my car, I could think about the forces then acting on the car. We would have a gravitational force. We would have a normal force that would be perpendicular to the surface. There would be some sort of propulsion. I'll just call that P, something that's powering the car forward. And then we would have our drag force. And we could have some rolling friction. So I'll just put that in here. So we're not asked to solve anything in terms of like acceleration or second law even. In this problem, we're really just asked to connect these two forces, and they're both going to be opposite the direction the car is moving. They just want us to know what speed does that drag force equal that rolling friction force, okay? So we're going to just set this up. We're just going to say magnitude of the drag force needs to equal magnitude of that rolling friction force. And then we've got little equations for both of these. So the drag force is going to be this equation up here. And then our rolling friction is going to be mu times the normal force. So this drag force is going to be 1/2. We've got our coefficient, we've got our density, we have our area, and then our v squared. And then our rolling friction is just going to be mu sub r and times our normal force. And our normal force here, if we look in this direction, so we should recognize that if a car is traveling along a horizontal surface and I only have the normal force in mg, the gravitational force in the y direction, then I should be able to say, so it's okay for you to say that that normal is equal to mg without setting up a whole second law starting equation in the y direction. I will say you have to be careful with that. If there is another force, if there's any other force in the y direction besides the normal in mg, then you probably should set up the second law in the y direction, just to make sure you account for all of the forces, right? If normal force and mg are the only forces, then we can go ahead and say that those two are equal. So this is what I mean by this. If there's no acceleration in the y direction, the normal force is just equal to mg. Okay, so in this problem, we are asked for the speed where this is true, that these two forces are equal to each other. So I'm solving for v. We have, I think, everything in here already. So I already wrote, we have our c was given, we have a, we calculated, we have density. Normal is just mg, and I have m here. The only thing, excuse me, that I don't have is that coefficient of rolling friction. We know that we're thinking about tires on a road. So I can actually hop back up. I'm going to scroll back up through these notes to this table here. And we're going to do rubber on the dry concrete. So that's going to be this 0.02. So we're looking at rolling friction for tires on a road. So that's going to be 0.02. So let me write that. Let me go ahead and write that over here. Mu sub r is 0.02. Okay, so that means I have everything actually. So I'm going to go ahead and just rearrange this stuff. So v squared is equal to mu sub r times mg times 2 over c rho a. And then everything in there we have, so I can plug all of that in. And if I plug all of that in, I get a 566. We need to take the square root. So this is going to give me 24 meters per second. So when the car reaches a speed of 24 meters per second, then that drag force is going to be equal in magnitude to the friction that's experienced due to that rolling friction force.